sometimes.
Yeah.
Okay, fantastic. So we are starting our final day, and we are very happy to start this with Djuna Croon from Durham University. Djuna will talk about black hole archaeology with gravitational waves, so very exciting and hot topic. So please, Djuna, take the stage and go ahead.
Yeah, thanks for having me. It's been a really nice meeting so far. I've attended most of the other sessions from the previous few days. They were really good. Nice and specialized workshop. So yeah, I'm pretty happy to start talking about some of the work I've been thinking about in the last few years. And we've got like a little update that I'm pretty excited about, which is actually not yet out, but hopefully sometime next week. So yeah, one thing that I should actually, like a little disclaimer that I should give you is that, of course, this workshop is called Young Stars, but actually I am actually going to talk about old stars, and in fact, actually also about dead stars, so the stellar graveyard. So like slightly off topic, but I think still quite relevant, and also kind of on the theme of some of the other talks that I've seen in the previous few days. Yeah, I also like, if you have any questions that throughout the talk, please just feel free to ask them, and I'll try to answer them as we go along, or otherwise I'll answer them at the very end. Cool. So the stellar graveyard is what you can call this kind of whole plethora, like all of these black holes that have been currently detected. And of course, we have quite recently become much better at observing black holes because of gravitational waves, of course. Before that, we were always kind of relying on black holes being in binaries with luminous objects, etc. So we did actually observe black holes before that, but now with the LIGO and Virgo and CAGRA collaboration and future gravitational experiments as well, we actually become better and better at observing black holes. And now there's already quite many. So this is after the first to the third observation run of the LIGO Virgo and CAGRA collaboration. And you see there's already like a really big group. I actually had to update this slides quite recently because I only had like O1 to O3A on it. And even between these updates, I can actually see the number growing. So it's quite impressive. And, we're learning so much about these black holes, and we can already, like, as I'm going to tell you, we can also use these black holes actually as a population to start to learn statistical things about, their origin. And I think that's very exciting. So one particular thing that I learned about only a few years ago that is, kind of the essence of like what led me into this kind of work is that there's some structure that you can expect in this type of population, and in particular the population of black holes that's formed through the death of these old stars. And that is, of course, that there's a minimum mass of black holes. It's not quite clear when that is, like if there is actually a gap between the lightest or the heaviest neutron star and the lightest black holes, but there's some people think there is, and like actually kind of the collaboration quite often labels it as there's a mass gap between here. So it will actually become clear whether or not that is the case. But then also that like these black holes formed through old stars, the death of old stars, if you will, there actually could be another mass gap, which actually is kind of at much higher masses. So I put it here at about between 45 and 50 solar masses. Could be some structure, some mass gap, and then like sort of a whole range of black hole masses for which you can't form them in this way. Of course, you can still form them through mergers, and that's why in this plane you see here all of these arrows ending here. And so you could actually form black holes through prior mergers, but through the death of stars, like we have some good reasons to believe that there is at least the existence of this other mass gap at higher masses. And so that fascinated me a few years ago, and like led me to look into this type of prediction, and what lies sort of at the foot of that, and like how does it work, and what can we learn about physics in this way. Okay, yeah, so that's what I'm going to talk about. Good. So sort of just to give you a little bit of an idea as particle physicists and people interested in, particles inside stars, where on the kind of typical plane of temperature, here temperature in Kelvin, but also temperature in keV for convenience here on the right-hand side. And like densities are we. So here's all these kind of typical objects that you might study. So I am actually mostly interested in like the evolution that takes place for these very heavy blue giant type stars that kind of like evolve here, both may sequence stellar evolution, burning through heavier and heavier chemical elements. So first they've already burned through all of their hydrogen and they're burning through helium, and then progressively helium, carbon, oxygen, silicon, etc. So kind of these really quite hot temperatures, also compared to, for example, like the helium flash, and especially compared to temperatures that like, stars like our sun will reach. So it's very hot and heavy objects and relatively dense, though not, of course, as hot and dense as like proton neutron stars, which would be somewhere over here, or maybe a little bit higher even. Okay, so let me just zoom into this kind of evolution. And just talk a little bit about what happens for particular stars of a particular masses. So let me zoom in and actually show you kind of some results of the type of thing that you would find if you simulate sort of stars with an initial mass on with the ignition of helium burning. Like if you run a stellar evolution simulation, such as one with MESA. And what you see here is again the same plane with the core temperature and the core density, and in 3 different stars with different, but all very heavy, like initial masses on the helium, like at the onset of helium burning. And so what you see is like as they evolve, as you might expect, they will get progressively hotter and hotter and denser. At some point, they will have burned through their helium and like ignite carbon, etc. But you see here, there's also kind of like some wiggles like starting to arise. Like not for the 40 solar mass one, this seems to kind of like fly straight through, but like some like this 71 especially seems here to have some sort of like pulse, and then this 120 solar mass one also kind of has this weird structure here. And so what happens in our simulation, and what do we think happens in the cores of these stars that gives rise to this type of behavior? Well, so first, like, this first burning stage, there's a few sort of thermonuclear reactions that fuel the star fuel, that keep it from collapsing, and that like release energy, these exothermic reactions. The first one called triple alpha. So you have these like 3 alpha particles, of course. So 2 helium particles forming a beryllium and then capturing another alpha and forming a carbon. And so this releases energy. And then there's this other process that's also important, is where so this carbon goes on and like captures another helium particle and forms oxygen. So in this stage, you burn helium and you form oxygen and you release energy, of course. And then in this further stage, you burn through carbon, and you can kind of have further oxygen formed and also helium formed. Okay. So one of the things that I haven't told you yet about this plane, but it's actually very important, is that there's this whole region here, which is like here labeled like unstable. And what happens here is that like, this is the adiabatic parameter of the core of the star, actually can reach these like unstable values, leading to core collapse. And why is that the case? Well, it's actually the case if you kind of remember from like my previous plot. I also compare, like, I don't know, maybe you actually are good enough to do this in your head, but if you go from Kelvin to EVs, or like particle physics units, then like you can actually convert between like the temperatures in the star here and these particle physics units. And what you'll find actually is that you're actually not that far away from the mass of an electron. So what actually happens is that like these temperatures in these stellar cores are so high that you actually can form from the plasma electron-positron pairs just through like through this process where you convert photons into electron-positron pairs. Now, this actually starts to happen, like below the, like for temperatures below the electron mass. because of course, like these things are formed in some sort of Boltzmann distribution, and in the tail of that distribution, you can already start to form some of these, even if they're kind of non-relativistic at production. But what happens then is that like you are actually converting something like photons, which are of course relativistic and actually they contribute to the radiation pressure of the core of the star, to something that's non-relativistic and actually just contributes to the mass. And these are these electron-positron pairs. And so that's exactly what happens in this sort of region, and that renders the star unstable. You're kind of converting something which gives an outward pressure to something that actually just contributes extra gravity. And it also tells you a bit for like about how this kind of region, the shape of the typical shape of this region that you would expect. Namely, like if you go to much higher core temperatures, some point you start to produce enough of these electrons relativistically, so they actually contribute to the radiation pressure. And if you go to too low temperatures, then this process is just too Boltzmann suppressed to actually significantly do anything to the star. And to the right, there's this extra like ionic pressure, which basically takes over and means that like you're not like dependent on radiation pressure to the extent that like this process is very important. But in this region and near this region, this is actually kind of an important thing that goes on, and it means that the core will start to collapse upon itself prematurely, if you will. And so then what actually happens is this kind of chain reaction, because I told you also that in these prior burning stages, I was forming oxygen, and this oxygen has this like explosive burning cycle. And so this explosive like oxygen burning can actually get triggered once you start to core collapse, and that happens in this region. So just to give you like an overview, like in a nutshell, what happens in this pair-instability process. So first I start with a star, which has like a very hot core at some point, so hot that I start to be able to produce these like non-relativistic electron-positron pairs in the stellar plasma, in the core plasma. Then these electron-positron pairs can trigger premature core collapse. Now, explosive oxygen burning is like then triggered and gets ignited. And then one of three things might happen, and what actually happens depends on the mass of the star. So for these very, very heavy stars, so you think about something that's actually 200 solar masses or something like that, there's actually the photodisintegration may take place. A bit more on that later, but like what it could do is like trigger immediate black hole collapse. And so you actually still have this like explosive oxygen burning, but all of these photons immediately get like reabsorbed, and you actually collapse immediately into a black hole. But for these like slightly lighter stars, still of course very heavy stars, what happens is that like explosive oxygen burning can unbind all of the material of the star, so it actually gives so much energy off that you actually have nothing that's gravitationally bound to the star anymore. All the material has the escape velocity, if you will, and you end up with nothing. And this is called a pair-instability supernova. And with these like slightly lighter stars, you can actually still like eject quite a lot of material, or some of the material, but not all of that. And you could even go through this cycle a few times for these very, very unlucky stars, if you will. And that's called pulsational pair-instability supernova. And you end up with a black hole, but that black hole might actually not be quite as heavy as you would expect. Okay. Sorry. And this is what it would look like, for a particular metallicity. What you would get is like here on the x-axis, I have these like initial star masses on the helium, at the onset of helium burning. And here I've got like the final black hole masses, especially these ones here on reds. And you see that here on the like left-hand side of this plane, this is kind of a nearly linear situation. So you actually end up with black holes that are kind of, that have a mass which is kind of equal to the initial mass minus like the stellar wind, the loss of mass in stellar winds. And then as you move to the right, there's this like pulsational pair-instability that kicks in, and you actually start to lose mass, and then eventually these stars completely explode. And so the immediate consequence of that is that there are no black holes that you form, in this whole region here above, It starts here at just above 40, and like here above, you don't form any black holes. Up until, if I would have continued these plots like to the right, at some point you would have like hit this photo disintegration instability again, and you would produce black holes again, and they would kind of more or less live on this like dashed line, the helium depletion mass. Again. Okay, just a little bit more about that photo disintegration, just because it's going to become a little bit more important in a moment. So what it is like the rapid absorption of very high energy photons by these other particles, by nuclei, and it leads to like a rapid decrease in the adiabatic parameter, and therefore a contraction. So you're again like, you know, kind of absorbing all of these high energy photons that you've just produced very rapidly, and then like you actually collapse. And so in these very, very high mass stars, oxygen burning like still, you know, happens and releases photons, but it can no longer keep up with the contraction that is due to photo disintegration. And therefore, like these very high mass stars, they won't pulse, but immediately collapse into black holes. Good, so and that will like give you this upper end of the mass gap. Okay, good. So you might think like, what does a BSM physicist like, you know, want to know about this? Well, like there's kind of like, what's interesting is that you're actually talking about regimes of this regime in the stellar plane where you have like very high temperatures, you know, hotter than most of the other situation that we've been thinking about, but still like relatively low density. And there's a few things that you can think about, and people have think about for new particles influence in this process. The first and like easiest thing is, of course, like you can think about producing these particles in the star and then free streaming out. It's also the easiest things like in terms of doing a simulation, of course, because you don't have to actually think about all these more complicated effects that we're now thinking about. So they might actually be heavier and more strongly coupled and like get trapped. And then that would really change the whole evolution of the star. They might also collect in the star and annihilate in the core, or they might have been there, you know, to start with. Maybe they seeded even like these stars. That's what some people have been thinking about a little bit. And then their annihilation might actually change something in the core, or they might modify other rates in the star, for example. Some people have also thought about like, you know, changing nuclear rates. Like you can actually sort of turn this whole problem on its head and say Pair-instability is a way to probe the formation of oxygen in the stars, in particular, this particular rate, which is also kind of a target for nuclear physicists. Or what happens if you change kind of Newton's constant of gravity in these stellar cores. So I'm gonna actually mostly talk about, like for the rest of this talk, before I start talking a little bit about, you know, how you would actually go about measuring this kind of second scenario where you produce particles in the star and they get trapped there, and what they would do to the star. Okay, some of the inspiration for this comes from these axions in the cosmological triangle. So this actually kind of this open region of parameter space here. It is kind of like where you have these relatively heavy axions, which with like a relatively large coupling, so coupling to photons. And there's this kind of triangle here, triangle-shaped region where you actually kind of like escape both these like other astrophysical constraints. This is of course to do with the fact with the temperatures that you reach in these stars. And then like you also kind of escape lab experiments at the moment. There's cosmological constraints that like you can set on this region, but that will depend a bit on your cosmology. Yeah, this is kind of the inspiration, but like what I'm going to talk about is not very specific to axions, just any type of particle that you can produce in the star to like, you know, with some kind of like abundance. Okay, so if you think about a particle, like a trapped new particle, that's like relatively heavy and relatively strongly coupled, if they remain in the star, what could happen is you actually change the stellar structure equations. And so if you wanna study that, you actually have to change the equation of state of the star. So this is kind of like something that we've been thinking about for a little while. but actually turns out to be like not a trivial thing to do. So it took us quite a while to figure out how to do this in the particular simulations that we were running. And yeah, I'll spare you all of the details. It will all kind of go in this huge appendix that we're writing for our paper. But you know, you kind of need to update all of these equation of states variables, like by giving them like contributions from this new particle. So like kind of like the target is like, what if like you have this, you know, you have this plane as I was showing you before with a core temperature and density, where you have this like normal kind of pair-instability region, and stellar evolution schematically just falls within this gray bands. Now, if I add like a bosonic particle to this, that means actually I have created this like extra region of instability, because I can also produce this particle, and it has a particular mass, and that extra region extends a little bit further. So this doesn't seem like a whole lot, like it seems like kind of a sliver, but actually it can have pretty dramatic consequences, as I'll show you in a moment. So this kind of like, I'm adding here this extra particle, and so the reason this region is bigger is because like now I'm adding this bosonic instability to this like existing instability from electron-positron pairs. So this is purely kind of like, you know, a calculation before I did any simulations or so. Now, preliminary results for if you run these simulations, so if you indeed do this kind of simulation of stellar evolution throughout this plane, is what I'm showing you here. So one thing to note, like from what I was showing you before, I was showing you like a relatively high metallicity. I think it was 1/10 of the solar metallicity. Now I'm actually thinking about really small metallicity, because I'm thinking specifically about, you know, for example, population-free stars. We're still kind of working on these like slightly higher metallicity stars. So that's kind of why this might look a little bit different from what you saw before. But yeah, and here, this is kind of the standard case for the standard model. Like you got this, again, like this initial star mass here and this like final black hole mass here. And what you're seeing is like, you've got this curve, and indeed, like you got this like, you know, black hole mass gap starting at like around about 47. It is like, I think it's 47.7 or something like that if you do this type of fits. And now if I add this like axions to my equation of states and do look more at something like a region like this, if you will, then actually you see that I still get the same qualitative behavior, but you see that actually this kind of instability becomes important for stars with far lower mass. And indeed, like actually it starts to be important already at like maybe 10 solar masses lower than it was here. And qualitatively, it's a similar behavior, but you actually see that these 50 solar mass stars already go through this axion instability supernova, as we're referring to it now, because it's not like a pair instability supernova, of course, anymore. Well, not strictly, at least. Sorry, I have a bit of a dry throat. Okay. Good. So good. Here's just an example. I just wanted to give you one example of a star actually evolving throughout this plane. Here's again this region, the standard model region, and this like a new region. And I'm showing you here kind of the evolution of a star. I've actually given you color-coded it for you, so that's easy to see. This is kind of the model number. It's not quite like the time variable, because it's like has a kind of an adaptive time step to simulation. But you know, like there's kind of a nonlinear relation between this and time. So yeah, you kind of like see here, you don't even need to like really kind of hit this region for this to like affect things. But here, this is the star. I haven't said it on the slide. This is a 50 solar mass star, so that actually already goes through this pair-instability, and you kind of like have this kind of like this type of pulse setting in here. Okay. One thing that's actually kind of interesting is that like, because this is happening for lower mass stars, what you might actually think is like, what you might want to compare is like the type of the actual luminosity of this event um, for like as a function of kind of like the solar masses, the initial star mass, if you will. So what I'm showing you here is like in yellow, this is this like stars with the new axionic particle contributions, like a 50 solar mass star. And you see this is here in a model number, like kind of what you can compare is like how high this kind of luminosity peak becomes compared to like this Pair-instability, like standard model like results for a much heavier star. And so you see that like as a function of star mass, you actually have a much higher, like larger luminosity. And of course, also this happens at like, lower masses. And so, if you assume, for example, that your initial mass function for your stars is something like a power law with a negative slope, like these stars are of course much more common than the 70 solar mass stars. And so in that sense, like actually these instability supernovas might be much more common, than you would expect if you just had like a pulsational Pair-instability supernova. Okay, so that's something we're also kind of thinking about at the moment. Okay. Then another thing, the last thing to notice is that like, so this is kind of something I already showed you, but now kind of condensed in this lower region of the plot, where you have here this like, in orange, this result where you also have these axions with an electron mass, and here just the standard model. So what's interesting is that what's also changing is here this higher region here, where you have this photodisintegration instability. So actually this photodisintegration instability also kicks in at lower masses. So you're actually kind of shifting this whole mass gap down a little bit. And this actually becomes also, more kind of likely that you would observe these heavier black holes in a gravitational wave experiment at the moment. So it's kind of interesting that you actually form like, you would form like lighter black holes above the mass gap in this sense than you would otherwise. And the mass gap is also slightly shrunk. Yeah, that's kind of also, but yeah, the more important effect is like here you form these like these black holes here. This is actually kind of like, almost 30 solar masses here between this. Okay. In the last few minutes, I just wanted to talk a little bit like, this is all well and good, but like, why do I think this is actually observable? Maybe not today, but someday we'll be better at this. And you'll note that I'm actually kind of decreasing my population size a little bit because I'm only taking into account these data sets for LIGO Virgo. It's from 01 to 03A. And there's now also this 03B, collection that's been publicly released. But that's kind of we didn't redo this analysis yet. We're working on it, so that's why I'm kind of like showing this for a smaller data set than is available at the moment. We're working on an update. But yeah, here is kind of like these black holes with an arbitrary x-axis, like these black hole masses that have been observed with error bars. And so how do you go about actually sort of like kind of looking at this? Well, of course, the first thing you could do is like look at the mass distribution of this data set, and you get something like this. The reason I've like given you like with and without this one event is because, especially at this time that this was the data sets, this was kind of an outlier event, very heavy black holes. And so you see that here, especially here in the tail, this mass function, this mass distribution really depends on whether or not you include this event or not. Of course, like the mass distribution is not all you have. You've got like access to a lot more, such as spin alignment, eccentricity, and redshift. All of these parameters can tell you a little bit more, especially about like the origin and the kind of formation history of the binary and its environments. And that actually also gives you useful information. But the most important thing for what we've been studying so far is the mass distribution. So that's what I'll focus on first. Okay. Now, everything that I've been showing you so far, like kind of has this type of form where I've got like on the x-axis stellar mass and the y-axis a black hole mass, and the prediction will look something like this, schematically, right? And so if I add some, add or subtract, or like if I do something with standard model, beyond the standard model particles, of course, this form might change qualitatively. It will look similar, but of course, it might kind of change like exactly where it turns over and how it turns over and stuff like that. And there's been many types of papers, like, some of which I was a collaborator on, others by other people, kind of studying what exactly might happen. But how we can use data to test it actually kind of relies on, how this will then lead to black hole mass distributions. And what's kind of lucky about that is that, you have this, because of this turnover kind of behavior, there's this kind of large range of like initial stellar masses, for which is only a small range of black hole masses, and though that leads to kind of a pileup. That's kind of neat. Formally, this would even kind of diverge. You get an actual divergent peak in the black hole mass distributions. Of course, like that's not like, really that realistic, but you would get such a pileup. And so what you can do is, like, if you assume an initial mass function for the stellar mass distribution, so for example, a power law is like a relatively good assumption, it seems, then you actually would get something that looks like here, where you've got this kind of fall off behavior, and then this pile up, and then this like, this cliff drop down. And here you don't form any black holes. And so that's a kind of a feature that you can then actually look for if you want. So it's not only just that like you have this kind of discontinuation that you would expect, but also this kind of like peak just before it. So we came up with like a way to actually fit this like in a very small number of parameters. That's kind of this functional form that I give here. Kind of it approximates a delta function in the limit that this is alpha is very small, if you will. Like it allows for more of these like pulsational pair-instability supernova in the peak here for larger alpha. And it turns out that this is kind of a good fit to the types of things you would expect from stellar evolution results. Anyways, so what you could do then is like you could use specific like predictions from your stellar evolution simulation, such as here, where you've got this like this type of qualitative behavior very similar, but actually quantitatively different. And some of these scenarios give you this actually, it's a bit weirder type of functional form. But you could actually kind of like, assuming that there is like an initial star mass distribution that's like a power law with a negative slope, can actually kind of predict what the black hole mass distribution will look like. And it has this kind of peak, and you can fit it to our specific function. So these are kind of scenarios that I haven't really talked about. This is a scenario I have talked about, this like axion instability supernova. And I'm showing you here this plot that you've already seen. And then here, like this black hole mass distribution here with this peak here. Fitted to our proposal, to fit to the LIGO data. I should say, like, when people often interrupt me and say, but actually you did also say that you can form these like heavier black holes like within the mass gap, like through prior mergers. And of course that's okay, that's true. But first of all, you would still have this kind of cliff drop type of scenario. It's not no reason to expect there's these are continuous. And then this peak thing you could also still look for. And then moreover, like, unless things are really, really strange, their mass distribution of these like secondary black holes would kind of inherit from this other mass distribution. So like, given some basic assumptions, this is, for example, something that you could get for a secondary mass distribution. And so you could actually, if you were like fitting for this, like with the LIGO data, you could just fit, like given the kind of shape of this, you could fit for a particular pollutant population, which is higher generational. And it doesn't preclude that you look for this type of peak. Okay, so this is like some old results. And as I was saying, like, we were kind of looking at, the new data, to increase this. But kind of what's encouraging at least is that like this mass function that we proposed gives you similar, very similar results as the best mass function that the collaboration was using, which is the power line peak mass function. And so you actually get this very similar base factor, you know, and this is with the full data set. And you see here that there's kind of like, it looks a bit like this is, you know, you don't see the peak very obviously here because this is like, you know, posterior distribution over many different, you know, many different parameters, of course, but it's kind of like roundabout here that you would see it. And then we also did it like without this event, just because it seemed like it might be a bit of an outlier, you know, at this time. And it will be interesting to see what happens, like given this larger data sets. Okay. Cool. So that's it. I think I talked my 35 minutes and there's time for a few questions now. Yeah, I just think gravitational waves are a super exciting new opportunity to study open questions. And I think actually what's really cool now is that we actually get access to this, to these stellar remnants and actually populations of stellar remnants, which then will allow us to sort of like think back and do a bit of archaeology, if you will, and think back about like the processes that lead to these stellar remnants. And one example of a process is Pair-instability supernovae, which is actually fascinating because it leads to this completely unpopulated space in the stellar graveyard, the black hole mass gap. And it's like a probe of new particle physics and nuclear physics, which will actually come to a bit more light in the future because this like data set is increasing so rapidly. So I gave you an example of like the type of black hole population study that you can do, you know, on this growing data set, which will allow you to look for these features to identify, you know, the edges of the black hole mass gap, and do this type of analysis, black hole archaeology. So thank you very much, and I'll take any questions if you have them.
So thanks a lot, Djuna, for the very nice talk. Of course, we have time for several questions from the audience. Let's see if anyone raise the hand. Let me look at the, otherwise I start actually. Mm-hmm. Okay, I can start while shy people go ahead and raise their hands. So at some point you showed some plot for the Axion, right? And you highlighted the cosmological triangle, and I was curious to see the result on that. So is your analysis ongoing analysis like do something interesting in that perimeter space?
Yeah, it's in that parameter space, like because that includes like electron mass axiom. So like we could have picked another mass, but we picked the electron mass because you can kind of directly compare two electrons. But yeah, like that mass is kind of included in this parameter space. And then this is the type of coupling that would actually, on the timescales that you're interested in, actually lead to like these equation of states variations. So we kind of checked that within our simulations, like, you know, these kind of changes were established on the time scale, like on a time scale that's smaller than the time step in the simulation, if that makes sense, with this type of coupling. So that's indeed within this triangle.
Okay. Another thing I think it also related somehow, because you're looking at stars and sometimes then it will become supernovae. For example, in our last paper with Georg, we actually closed this mass gap with some reasoning that is kind of similar like to this equation in the sense at some point it's not really similar, but you inject energy because you're very efficient at this coupling. So we can talk more about that offline, of course, but and that you know, just if you want to do also like, let's say, benchmark point, you may also want to explore different masses and stuff, because I think we are quite confident that region is already excluded, I would say, from supernova physics only.
This region, you would say this region.
Yeah, because like there are, you know, especially if you look at low energy supernovae, they present very, very small energy. And as you say, for this coupling and mass, you know, the kind of like interaction are becoming and decay and stuff are becoming like also like effective. Okay, so this region is just by energetic argument excluded, let's say.
Okay, well, I have a look at that. But, yeah, thanks. You should send me.
Yeah, that will be interesting to cross check, of course, anyway. But if you are also powerful to go into other masses, will be also interesting. Okay, so any further questions from the audience? Otherwise, I have another one actually, but okay, I go ahead. So I take profit of my position of host.
Yeah.
And so you already mentioned this kind of merger, right? In that case, you argue that even if you have the post merger, let's say second generation, you can still like have an hint of your process, right? But what about other astrophysical uncertainties, right? That as far as I know, at least talking to astrophysicists like doing gravitational waves for this mass gap, right? There are many really explanations that have that can have a lot of uncertainty, like metallicity, you know, like time of formation of these pop 3 stars that is very uncertain, you know, when it's happening, when it's stopping, right? We just have some bounds and limitation from reionization and stuff like that, right? So I was wondering if your analysis, because of some particular feature, is kind of blind to these uncertainties, or you just have to live with them?
Yeah, no, I mean, you're right that there's, I mean, I think the most important one is this like nuclear rates actually.
Right, for example.
So it's just like the rate of converting carbon to oxygen. Metallicity makes a difference as well, and we're doing this analysis for different metallicities as I was mentioning. But typically the bigger one is actually the nuclear rate. So this is kind of what this is, right? So like if you change like this rate by like 1 or 2 sigma, then you actually shift. Then you shift this prediction, and that also gives you like a shift of like the peak. You still like, I mean, qualitatively it looks the same, but you get it. You do get a shift. So yeah, I mean, this is the degeneracy you just have to live with. Of course, if you have a very, very different kind of shape of your mass function, then you might hope to predict something like that. But yeah, in terms of actually looking where this like mass gap starts, there's this dependence, and this is the biggest one. Metallicity will also change this by a little bit, but not as much as this will this rate will. Yeah.
And in terms of like shape, do you have an idea of how many? And so at the end of the day, also how far in the future you will have so many data that somehow, I've been using also like this data, and they, from release to release, the mass function change a lot, right? So do you have an idea of how many data or how many years you have to wait in order to really look for this kind of feature, and not just for the let's say the mass?
Yeah, it's a good question.
It's difficult to say.
I don't know if I'll burn my hands on that question yet, because like I want to, just because we are actually now like looking at O3b as well, and there's kind of like a factor 2 between the size of the data set between those samples. So I'll see like what happens to our posteriors in that time. But yeah, the as you know, like the size of the data set is actually increasing, like in an expanding way, because like the textures become so much more sensitive between these observational windows. So yeah, I don't know, it could be a few years, it could be longer, like but yeah, I want to actually see what happens to our posteriors like between these 2 data sets, and then I think I'll have a sharper answer to that question.
Okay, good. I will be back to you after your paper.
Yeah, sure. Yeah.
Okay. Yeah. Any final question for Djuna? Let's see. Everyone is shy. Okay, if there are, Eduardo.
I can ask a question. Can you go back to the cosmological triangle slide just to understand something in terms of mass? Because on the top of my head, I don't remember the values of the couplings and the masses. So this is like 1 kV, 10 to minus 5, 10 to minus 4. So you are producing them by Primakov in this star?
Yeah.
I see. No, I was okay. No, I was just wondering what happens with different particle physics models. That was I just have to think about it.
Okay, that's fine. Yeah, that's okay. Yeah. Yeah, I should say like what we're doing, like we're just adding a boson, like so it doesn't necessarily. Why this matters is like what the mass is, the masses that you put in it. But the code we're writing, the biggest assumption is that it's bosonic. So, and we will also release it. But yeah, this is kind of like an example that we were looking at.
I see.
But
so,
why Primakov if the temperature is large and the mass is like, let's say, few keV? I mean, depending on the temperature, of course, the temperature is a bit lower. I don't remember the temperature, but
it's very large.
Coalescence be important? No?
Yeah, I mean, we compared a few different processes. I mean, like now I need to think about like the relative. Sorry, I don't remember exactly which one was dominating.
Because there was also a paper like today, actually, no, by Giuseppe Lucente and collaborators, in which they were also considering coalescence, and that was kind of shifting some bound and was kind of relevant in this mass range. So probably. It was the first on the list on the F3 today. So also,
okay,
I'm not. It depends, of course, on the density and temperature of your mesa, like star that you were considering. But the coalescence could be relevant, I think. So I would.
I have a look at
in particular, considering how large is the temperature compared to the density. So it's very likely that perhaps coalescence will dominate.
Yeah, that's why exactly. So it would be good to check.
Okay, I have a look at that.
Well, thank you.
All right, thank you.
Okay, thanks a lot. I think that we can stop the recording.